Hi folks, we're going to take a look at number 13 from page 368. So they want us to show that this equality is true for all values of a and b that are greater than 0. Okay, so first of all, let's talk about these conditions, why we need them. Well, if you look at the exponent here, we see that we have logarithm of a and log base 10 of a, to be precise, log base 10 of b, and we know that logarithmic expressions are only valid for positive inputs. So that's why we need a and b to be greater than 0. All right? So we need to show that this is always true. So it's not like I'm solving an equation. I need to show that if I start with one side of the equation, it's always going to be equal to the other side of the equation. So essentially, we're proving an identity. All right, and usually the way to start is to start with the more complex side, the one that offers more algebra that can be done. So clearly that's going to be the right-hand side. So that's where I'm going to start. So I have my right-hand side is equal to b to the log a over log b. Okay, and remember, these are log base 10. Now, this is where I look at that exponent, and there really isn't any exponent rule that I can think of using that would be useful to me. But I want you to take a look at this expression and see if it's familiar. Okay, you see log of a over log of b. This looks a lot like the change of base formula. So let's recall the change of base formula. Change of base formula says that I can take the logarithm of any base of some input, and I can rewrite that using any other base. So that can be written as the log of b of x. Okay, so log new base of the original input divided by log new base of the original base, log a. And in particular, I can choose this to be base 10. So log x over log a. So this is the property that we found, the change of base formula. So I'm going to look here and I realize that I can rewrite the numerator as, well, this is log base 10 of, well, a would represent the original input, and log base 10, this would represent the original base. So this exponent here can be rewritten as log base b of a. Okay, so again, notice that this is just an application of this change of base formula. This logarithm here can be written as log of the original input divided by log of the original base. All right, but now that I've written this in the form that I have here, I notice that I've got inverse functions, because this is the function b to the x, this is the function log base b to the x. When I apply them consecutively, they cancel each other out. All right, so this here is just going to be equal to the original input, which is a, which is exactly our left-hand side. All right, so just to recap, is we want to start with one side of the equation, manipulate it, and show that it's equal to the other side of the equation, regardless of the values of a and b. And the trick here was to notice that this could be interpreted as a change of base, with a representing the original input and b representing the original base. And then I just applied our property of inverse functions. All right, that's it for this one.